Now let's see some examples for DFA. Given some language, how to construct the DFA. Construct DFA for set of all strings beginning with A over the alphabet sigma equals A comma B. Given alphabet is sigma equals A comma B, the language consists of strings beginning with A. So the language contains strings such as A followed by A followed by B, A followed by A followed by AB, and so on. This is an infinite set. So in the very beginning, automata will be in its initial state. Let the initial state be Q0, represented by an arrow pointing to it. In this initial state, automata is expecting for strings beginning with A. So in this state, automata remembers that the first input symbol is not yet seen. When the first input symbol is seen, if that input symbol is A, then automata should move to another state Q1, which remembers that the string has already started with A. And such strings are to be accepted. So Q1 should be an accepting state or final state. So if the machine is in state Q1, it means the string has already started with A. So if the following symbols are any number of A's or B's or their combination, the machine should remain in the same accepting state Q1, remembering that the string has already started with A. Now we can see string A is accepted, AA is accepted, AB is accepted, A followed by AA is accepted, A followed by AB is accepted. Every string beginning with A is accepted. But this is not a deterministic finite automata yet, because from state Q1 for every possible input we specified the transition, but from state Q0 we specified transition for input symbol A. We didn't specify transition for input symbol B. When the automata is in its initial state, if the first symbol found is B, then what should we do? Those strings are to be rejected because they didn't start with A. So, if the first symbol found is B, we can move the machine to a state called dead state or trapped state. A dead state or trapped state is a state from which there is no possibility of reaching the final state or accepting state. If a string begins with B, then there is no need of moving the machine to the final state. So we can move the machine to a dead state or a trap state. So this state actually remembers that the string didn't start with A. So if the machine is in state Q2, it means the string didn't start with A. So if the following symbols are any number of A's or B's or their combination, we can reject the string. So let the machine remain in the same dead state or trap state. Now we can see the empty string epsilon will be rejected. String B is rejected. B followed by A is rejected. B followed by B is rejected. B followed by any combinations of A's and B's are rejected. And this is a deterministic finite automata. We can represent it using the phi tuple Q sigma delta Q0 F. Q consists of the states Q0, Q1 and Q2. Sigma contains input symbols A and B. Q0 is the initial state. F consists of the set Q1. We can define the set of transitions delta Q0A equals Q1, delta Q0B equals Q2, delta Q1A equals Q1, delta Q1B equals Q1, delta Q2A equals Q2, delta Q2B equals Q2. Now construct DFA for set of all strings beginning with AB over the alphabet sigma equals A comma B. Given alphabet is sigma equals A comma B, language contains strings such as AB, AB followed by A, AB followed by B, AB followed by AB followed by AB, and so on. This is an infinite set. In the very beginning, automata will be in its initial state Q0. The Q0 now remembers that the first substring, the beginning substring AB is not found, and automata is expecting for the substring AB. If the first input symbol is A, then automata should move to another state Q1, which remembers that the string has started with A. Now it is expecting for B. As per expectation, if the next input symbol is B, then automata should move to another state Q2, which remembers that the string has started with AB. Such strings are to be accepted, so Q2 should be an accepting state or final state. If the machine is in state Q2, it means string has already started with AB. So if the following symbols are any number of A's or B's or their combination, let the machine remain in the same accepting state Q2, remembering that the string has started with AB. Now from state Q0, what happens if the input symbol found is B instead of A? If the input symbol found is B, it means the string begins with B. Such strings are to be rejected. So we can move the machine to a dead state or trap state. Thus this state remembers that the string didn't start with AB. Now from state Q1, what happens if we find the symbol A? It means the string has started with A, but instead of B, the next input symbol is A, means the string has started with AA. Such strings are also to be rejected, so we can move the machine to the dead state or the trap state. Now, if the machine is in state Q3, it means the string didn't start with AB. So if the following symbols are A's or B's or their combinations, then let the machine remain in the same rejecting state Q3, remembering that the string didn't start with AB. So state Q0 remembers that the beginning substring AB is not found. Q1 remembers that the string started with A. Q2 remembers that the string started with AB. Q3 remembers that the string didn't start with AB. So for every state, for every possible input, we have specified the transitions, and this is a DFA. Now consider this question. Construct the DFA for set of all strings beginning with BAB over the alphabet sigma equals A, B. The language consists of the strings BAB, BAB followed by A, BAB followed by B, BAB followed by AA, and so on. This is an infinite set. In the very beginning, automata will be in its initial state Q0, expecting for the beginning substring BAB. As per expectation, if the first input symbol found is B, then move to another state Q1, which remembers that string has already started with B. Now it is expecting for A. As per expectation, if the next input symbol is A, move to another state Q2, which remembers that string has started with BA. Then, if the next input symbol found is B, move to another state Q3, which remembers that the string has started with BAB. Such strings are to be accepted, so Q3 should be an accepting state or final state. If the machine is in state Q3, it means string has already begun with BAB. So if the following symbols are A's or B's or their combination, let the machine remain in the same accepting state, remembering that the string has started with BAB. Now from state Q0, instead of B, what happens if input symbol A is found? It means the string has begun with the input symbol A. Such strings are to be rejected, so move to a trap state or dead state Q4, from which there is no transition to the final state. Then string started with B, but against the expectation, next symbol was B, means the string is beginning with BB. Such strings are also to be rejected, so move to the trap state or dead state. Now the string started with BA and machine is in state Q2, but instead of B we found an A. Then it means the string starts with BAA. Such strings are also to be rejected, so move to the dead state or the trap state Q4. So state Q4 actually remembers that the string has not begun with BAB. So if the following input symbols are A's or B's or their combinations, then let the machine remain in the same rejecting state Q4, remembering that The string has not begun with the substring BAB. So we can see string BAB is accepted, BAB followed by A is accepted, BABB is accepted, BABAB is accepted, and so on. Every string beginning with BAB is accepted. And the other strings such as epsilon is rejected, strings beginning with A is rejected, strings beginning with BB is rejected, strings beginning with BAA are rejected, and so on. So for every state, for every possible input, we have specified the transitions, and this is a deterministic finite automata.